Hi, this is Math 2520, and this video is over section 6.6. And we are looking at using integration and calculus to find surface areas of solids. And so that's the main point of this video. One thing is when I write the surface area, I'm just going to write A for area. We gotta know in this chapter we're just dealing with surface area, so A will always stand for the surface area. And the surface area is the area of basically outside the solid, or adding up all the sides of the solid, basically all the areas of the solid that it makes up. So like a cube has 6 faces, it's the area of each of those faces added together. So for a cone, the surface area is found by pi r l, where L is your diagonal and R is your radius. And again, this is surface area. And this particular thing is not including the base. So it's, imagine like making a cone out of paper where you still have the base kind of open. That's kind of how it is for this. Otherwise, we would add on. If we include the base as part of it, then it's pi r l plus pi r squared for the base. Okay, but we're not going to include the base. That was a horrible cone too. Anyway, so let's now look at one a little bit more complicated. You have a cone with 2 different radiuses as it shrinks, and so you have 2 different L's there, L1 and L2. So kind of a cone on top of a cone. So if we're looking at, let's say, just this section here, as that surface area, then what we're going to do is we're going to take the whole cone surface area minus this section of the surface area to get that other piece. Alright, so this is going to be pi r1 L1, surface area of the whole thing. Oh, plus L2. Almost forgot that. That's the surface area of the whole thing minus pi r2 L2. Alright, now doing a little bit of algebra, we'll get pi times r1 L1 minus, oh actually I don't want to do it like that. Do this, r1 minus r2 L2 plus r1 L1. Okay, now this comes from basically distributing the r1 to on the pi to L1 and L2, and then putting the L's 2 together, so you have R1 minus R2, and you're pulling the pi all the way out and you're pulling the L2 out, and then you have R1 L1 also. So just kind of distribute and then pull pieces out as you need to. But it's just algebra there. Now if we look at sine of alpha being, if this is your vertical, this angle here, that is your alpha. It's going to equal R2 over L2. R2 being your radius, L2 being your diagonal. Make that better too. And it's also going to equal R1 over L1 plus L2. Now what we're going to do here is we're going to take this part and adjust it so that we can do a substitution in for this. Okay, so we do a little algebra here. R2 is L1 plus L2 equaling R1 L2, and then distribute R2 L1 plus R2 L2 equals R1 L2, and then we're going to put together we're gonna pull out L2. So we gotta get the L2s together. So subtract that over. So I have R2 L1 equals R2 L2 minus, oh, I'm sorry, that should be minus 1. R1 L2 minus R2 L2. So I just moved this one over to this side, or subtracted it over. And then I can pull out L2. So I have R1 minus R2 L2, which is what I have up here. Okay. And so then this area will become pi, and then that part we're substituting out is just R2 L1 plus R1 L1. That allows us to then, that should be minus sign. Oh, plus sign, okay. So I question myself. R2 plus L1 L1. Okay. And then what we're going to do is, instead of having multiple R's, we're going to let R equal R1 plus R2 over 2, which is going to equal, when we plug this in, 2 pi R L, and we're going to also let L equal L1. Right, so now when we're looking at evolving this around an axis, right, so if we look at this function from A to B, and we're going around this, so something like this. Your radius is from that axis to the function. Okay, so R is your f of x. And then your slant has to do with the side itself. Right, so you're going to look at this as a section of a cone with slant L and radius R. And so we'll have area is pi, and I'm going to switch this color, pi R1 L1 plus R2 L2. Or we can look at this as, again, 2 pi R L1, where R is your function, f of x, and L. Right, so when rotating around the x-axis, we always have 2 pi f of x L, or y L, if you want to think of it as just the y value. And we can do this either with respect with x or y, for arc length. Right, so we'll look at integrating with respect to x. Your surface area is going to be the integral from a to b of 2 pi y square root of 1 plus dy over dx squared dx. Well, y, you don't have the function in terms of x, so y equals f of x. And then if we're doing it with respect to y, it's going from c to d, 2 pi y square root 1 plus dx over dy squared dy. And here your function is going to be from, you know, x equaling g of y or f of y, if we want to call it that. Alright, so let's set up an integral representing the surface area obtained by rotating about the x-axis. So this is going to be x equaling y squared over 9 plus 2. So I'm going to solve this for y squared. So x plus, where did I get that color from? Alright, x plus, I'm sorry, x minus 2 equals y squared over 9, so y squared equals 9x minus 2. And so y equals square root of this, so 3 square root of x minus 2. So then y prime is going to be equal to 3 over 2, and then square root on the bottom, x minus 2. Okay. So now surface area. Now we're going from 3 to 6. Two pi, and y is 3 square root of x minus 2, and square root of 1 plus 9 over 4 x minus 2 dx. Oh, and oh yeah, I did square that. Okay, so that's dx, I'm sorry, dy over dx squared. So you're squaring this 3, you're squaring the 2 to get 4, and you're squaring the square root of x minus 2 to get just x minus 2. Alright, so here we can keep going. 3 is 6, 2 pi, 3 square root of x minus 2, and then 4x minus 2 plus 9 over 4x minus 2. Just find a common denominator there. I can pull the 4x minus 2 out. And it's going to be kind of like, why are you doing this? But you'll see. So I have 3 square root of x minus 2 on top. Take the square root of the bottom to pull it out. You get 2 square root of x minus 2. So I just have the top now. And then those x minus 2's cancel, which is why I did it. And so also that 2's cancel, so we have 3 pi, cancel, 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 and cancel. And then this would be square root of 4 x minus 2 plus 9 dx. Okay, so now I'm going to distribute inside here. So I'll have 4x, and then minus 8 plus 9 will be 1, so plus 1. this is something I can take the integral of. So when I do, I'll get 3 pi times 2/3 and divided by 4, 4 being from the chain rule, not the square root. 4x plus 1 to 3/2. Evaluate from 3 to 6. Alright, so some things cancel out here, 3, 3, and this drops down to 2. So I get pi over 2, 4x plus 1 to 3/2, going from 3 to 6. Alright, so at this point, we can plug in the 6, we can plug in the 3. What you're going to end up with would be 122.72. So plug in the 6. I'll write that out first, but I'll write down the answer after this. So pi over 2, 4 times 6 plus 1 to 3/2 minus pi over 2 4 times 3 plus 1 to 3/2. And this is going to equal 122.72. Now, we can do this also by integrating with respect to y. And so here we have x function. We don't have to solve for x, but we do have to take the derivative, which will be 2/9 y. And so the surface area then becomes integral. And we want to know where our y goes to. So I'll have to figure that out here. But you'll have 2 pi y square root 1 plus 2/9 y squared. The whole thing should be squared. 2/9 y squared. Alright, now to get your limits for 3, we just plug into an equation. So for 3, you'll get 3 squared is 9, 9 over 9 is 1, which is plus 2 is 3, so 3 goes to 3. 6, you'll get 36 over 9, which is 4, and so you'll go 6. So actually the limits don't change here. I was actually wondering that when I was looking at my notes too. I'm like, I didn't change the limit. I wonder if I made a mistake. Well, I didn't. It just surprisingly works out to be the exact same limits. Alright, so integral from 3 to 6, 2 pi y, 1 plus 436 y squared. And this would be not 36. I multiply it by 4 because I got 4 on the top. 81. 9 squared is 81. Alright, then I'll multiply top and bottom. Well, find a common denominator. So 81 plus 4y squared over 81. Okay. I can pull the a1 out. When I pull it out from the square root, I divide by 9. I get 9. And it's in the denominator, so I have a1 plus 4y squared. Right. This one in particular, I can solve it through a u substitution. U equals a1 plus 4y squared. So du is 16y. Oh, I'm sorry, I squared that. 8y dy. And so this will become integral 2 pi over 9 and over 8. And then your du is your y, and I forgot to write it, but your dy. Those two things. And then you have square root of u. And then du. Alright, so we can solve this. So we'll end up with two pi 9/8, and then this is 1/2, so it goes up to 3/3, and you'll be dividing by that, so you'll be multiplying by 2/3. And this is going to be evaluated, which I haven't found the new limit, so I'm not going to write them. So we'll just do a to b for right now, because I'm going to be plugging back in what I had for u. I want to simplify this though first. So let's see here. This 2 will cancel out with that 8. Well, this 2 and this 2 times, so you get 4. So this cancels out with this, but you'll have a 2 then. So it reduces down to 1/2. That cancels with that 2. And so 27 times 2 will be 54. So pi over 54. And then I'll bring back my what I have for u, which was 81 plus 4y squared, the 3/2. Okay, which means I'm still evaluating this from 3 to 6. Alright, so when I do the evaluation of pi over 54, 81 plus 4 times 6 squared, all that to 3/2, minus pi over 54, 81 plus 4 times 3 squared, all to 3/2. And this will also come out to be 122.76. Okay, so both of these are rotating around the x-axis. So they're the same shape. So the fact that they come out to be the exact same surface areas makes sense, because we're just doing the math a little differently. We're not doing a different shape. Now, if we look at one rotate around the y-axis, let's pretend I'm drawing this parallel or mirrored for that matter. It'll look something like this. You know, you'll have it, you have a different shape because it's going on the y-axis. All right, so for rotating around the y-axis, it's going to be very similar formula: 2 pi xl or 2 pi f of xl where your radius, you know, is from the function to this. And then your L is this way. Okay. So way we will write the surface area if we're integrating 2 pi x times the square root of 1 plus dy over dx squared dy. And that's when we're doing it with respect to x, and when we do it with respect to y, then in the integral it's 1 plus dx over dy squared. So dy over dx, or your derivative of your f of x, and your dx over your dy, or your derivative of your f of y, goes here. Do color. So f of x, f of y, derivatives. Alright, so let's say we want to set up an integral that finds the surface area obtained by rotating about the y-axis with respect to x equals, with respect to y, for the function x equals square root of y minus 1, and it's going to be for y from 1 to 2. Alright, so this is respect to y, meaning we're going to look for f prime of y. So if x is square root 1 minus y minus 1, then x prime is going to be 1 over 2 square root of 1 minus 1, y minus 1. Okay, so our integral from 1 to 2 is going to be 2 pi x I use y there. Where did I find it? You're supposed to use x's. Let's give me 1 second here. Okay, yeah, I have to do the substitution. Okay, I just want to make sure I was right. Alright, so 1 plus 1 over 4 y minus 1. That's 2 squared. That's this squared, basically. So I squared the top and bottom. dy. Right, now for x's, I need my x in terms of y. That's why I was checking. I was wondering why I didn't have it like that at the beginning. But I just substitute this in. So it's an easy adjustment. Square root of 1 plus 1 over 4y minus 1 dy. Alright, so now I can find a common denominator. So I have 4y minus 1 plus 1 over 4y minus 1 dy. And then when I bring out the 4y minus 1, things are going to cancel. So has to save. So I have 2 square root of y minus 1 times square root of 4y minus 1 plus 1. And things cancel. That cancels with these. So integral from 1 to 2 of pi square root 4y minus 1 plus 1 dy. Okay, so I use a u substitution here as well. 4y minus 3. That's, let me take that one more step further. 4y, when I distribute the 4, I get 4y minus 4 plus 1 is minus 3. Right, so that's why I'm using that u substitution. And so du equals 4 dy. So dy equals du over 4. So integral from a to b, I'm changing my unit, so I'm not going to put new ones there. Pi square root of u, and then du over 4. Okay, so now when I integrate that, I'll get pi over 4. That goes up to 3/2, so times 2/3. U to 3/2. Integrated from a to b. And then certain things cancel, so 2, and that cancels, so we'll have pi over 6. U to 3/2 from a to b. And then we'll bring this back to using our u substitution. So 4y minus 3 to 3/2 from 1 to 2. Okay, so this goes to pi over 6, 4 times 2 minus 3 to 3/2, minus pi over 6, 4 times 1 minus 3 to 3/2. Be 8, 5 to 3/2 minus 4 minus 1 to 3/2, so that'd be just 1, so minus pi over 6. And you should get then, as a rounded answer, about 5.33. Right, this next one we're going to integrate with respect to x, and our function will be y equals 1 plus x squared. So with y equaling 1 plus x squared, dy is going to equal 2x dx. So we'll start this out. It's going from 2 to 3, 2 pi x square root of 1 plus, and remember this is your dy over dx. So that's squared, so that'd be 4x squared dx. And we don't have to do a whole lot of simplifying here. We'll let u equal 1 plus 4x squared, du equaling 8x dx. So I'm going to divide both sides by 4. Du over 4 equaling 2x dx. That will then count for the 2. Basically, I'm canceling without canceling. 2x and dx. Okay, so I have from a to b, pi, 2x dx is du over 4, so pi over 4, square root of u du. So take the antiderivative, you're going to multiply by 2/3, this will go up to 3/2. This again from a to b, and so this cancels here. So we end up with pi over 6, and then our u is 1 plus 4x squared, the 3/2, from 2 to 3. So we'll have pi over 6 times 1 plus 4, 3 squared to 3/2, minus pi over 6, 1 plus 4 times 2 squared to 3/2. And this should come out to be 81.14. Alright, so some guidelines for doing these. First, sketch a general idea of the curve. Identify where you're rotating this about. Determine if we have 2 pi x or 2 pi y. So basically, are you going to be integrating with g of y or f of x? And then based on that, and with respect you're taking your derivative to, you take the corresponding arc length formula, so the 1 plus f prime squared, or the 1 plus g of y prime squared. So you'd be finding your derivatives of either g of y or f of x, depending on which one you're choosing. And so we rewrite these so you have either r x's or r y's, and then you integrate. You can either integrate using a Desmos, or if you have certain integration techniques that we've covered that are easier to just do, we can integrate that way. We'll get a couple more problems and then an application problem. I suggest trying these next 2 first, and then come back to watch the video, see what needed to be done to get this to actually work. If you didn't get an answer or you weren't sure if it was right. Alright, so here we're going to find the surface area obtained by rotating the curve defined by the function y equals square root of x from 0 to 4 about the x-axis. We're going to differentiate with respect to x. Alright, so the area will be 2 pi. It'll go from 0 to 4. And you can always bring that 2 pi out in front. We'll choose y and find 1 plus dy over dx squared, since we're doing with this respect to x, dx. Alright, so y is square root of x, so dy over dx is 1 over 2 square root of x. So we're squaring that. The y itself, since we're doing this with respect to x, we need to do a substitution for y. Okay, so this y, let me be clear, the fact that we're going with the x-axis means I start with that y. Okay, I can't just start with an x. The fact that we're doing it with respect to x means I have to do dy over dx. Okay, the dy over dx means I have it in terms of x, so I need to change that y to in terms of x. So I can use y equals square root of x because I know that is true. So here we'll have square root of x times the square root of 1 plus, and then our dy over dx squared, so 1 over 4x dx. Alright, so a lot of these you should notice I'm finding common denominator right off the bat. So I have 2 pi from 0 to 4 square root of x square root of 4x plus 1 over 4x dx. Then take out the denominator. So I have square root of x over 2 square root of x 4x plus 1 dx. And then these cancel. You can always also bring in the square root of x kind of into the square root if you need to. That can also get to cancel. So let's see, we have 2 can cancel too. So pi, let me cancel those. The fact that it was on the outside threw me off. 0 to 4 square root of 4x plus 1 dx. And so we'll do a u substitution. U equals 4x plus 1 du equals 4 dx. So dx is du over 4. So this becomes pi from a to b square root of u du over 4. And so when we integrate this, we'll get pi over 4 times 2/3 u to 3/2. Integrating from a to b. And then we'll bring in our u so we can bring in our limits again. So pi, let's see, this is be 6 on the bottom. 4x plus 1 to 3/2, integrated from 0 to 4. Alright, so pi over 6. When I put 4 in there, I'll get 17 to 3/2. I put 0 in, I get 1 to 3/2, which is just 1, which is just pi over 6. Alright, so if we plug this into a calculator, we'll end up with 36.18. Alright, so the next one. We're doing a surface area obtained by rotating the curve defined by the function x equals yq minus 2 from 0 to 2 about the x-axis. So again, about the x-axis, meaning I'm using a y. We're going from 0 to 2. And because they give me my y limits, my y limits going from 0 to 2, I want to do this with respect to y. Right, and so I'm going to take x prime, be 3y squared dy, and so I'll have square root of 1 plus dx over dy squared. So in this case, I don't have to change my y. I'm going to have everything in terms of y. I do have to insert this, so I have 1 plus 9y to the 4th dy. Okay. And so something like this, I can, and this is one of the last ones, so I'm going to do this. I'm going to plug into Desmos. So to plug an integral into Desmos, function, find your integral. It goes from 0 to 2 pi y square root of 1 plus 9 y to the 4th. Oops, or dollar sign. D, oh, gotta be outside of that, dy. And gives you your value, 77.32. Alright, one last question. I know this video may be getting a little long. This chapter is a difficult one, so the videos go a little longer. This is going to be an engineering type problem. Engineer is designing a cylindrical water tank that will have a curved surface formed by rotating a parabolic shape about the the vertical axis, the y-axis. The equation of the parabolic curve that defines the profile of the tank is given by y equals 1/4 x squared, where y represents the height of the tank in meters and x is the horizontal distance from the axis of rotation. The tank is constructed to hold water up to a height of 3 meters. The engineering needs to determine the total surface area of the tank, including the curved surface and the base, which is flat and circular. Alright, so we have a couple of things. Y equals 1/4 x squared. So we can find dy dx, which is going to be 1/2 x. Okay, and that tells me I'm going to be doing this with respect to x. So if I'm doing it with respect to x, my integral is going to be 2 pi a to b x square root 1 plus dy over dx squared dx. I'm also the 1x is because of how I'm rotating this. Trying to see where it says. Oh, it says about the vertical axis. Right, and so if we go back, remember, if we're going about the y-axis, that's where we have our axis. So that's why the x is there. Just want to make sure I define that. All right. So we are rotating this curve from 0 to 6. So we'll have 2 pi 0 to 6 x. And we'll have the square root of 1 plus 1/4 x squared dx. Okay, we're going to do a u substitution. So u equals 1 plus 1/4 x squared. So du will equal 1/2 x dx. And so we can say 2 du equals x dx. Right, so the surface area is going to be 2 pi a to b. X dx is our 2 du, so we'll have another 2 on the outside. Square root of u du. So we'll have 4 pi, and we're going to do the integral here. 4 pi u to the 3/2 times 2/3, or divided by 3/2, so it would be multiplying by 2/3. And it's going to be from a to b. Alright, and so we'll have 8 pi over 3, and then 1 plus 1/4 x squared to the 3/2 from 0 to 6. Alright, so we end up with 8 pi over 3. Alright, so if we put in 6, I'll get 36 divided by 4 is 9, plus 1 is 10, so 10 to the 3/2 minus 8/3. I'll just get 1. And if I plug this in a calculator, I get about 256.54. Okay, so that's the calculated surface area of the curved part of the tank. Okay, now we want to calculate the area of the base. So this is A. B is a little easier. It's a cylinder, so A is pi r squared, r being 6, since it goes from 0 to 6, so pi 6 squared, 36 pi. And we can get a number for that, but I'm not going to. And then C is we're just combining this area, so 36 pi plus 256.54 is 369.64. Alright, so that's the end of 6.6. The next video and the last video in chapter 6 is going to be over 6.7, which is some physical applications with these integrals. Alright, I'll see you then.